What if I told you that you, me, and every form of life on Earth might have come from space? No, this isn't science fiction. This is a serious scientific theory called Panspermia, which has captivated some of the greatest scientific minds throughout history. The very essence of who we are and where we come from might be far more extraordinary than we ever imagined. Picture this. In the vast expanse of our cosmos, life might be traveling between worlds like seeds carried by cosmic winds. Just as a dandelion seed drifts through the air until it finds fertile soil, microscopic life forms could be hitchhiking on meteorites, asteroids, and space dust, spreading the seeds of life across the universe. This captivating idea forms the foundation of the panspermia theory, suggesting that life on Earth might have originated from these cosmic travelers. The implications of this theory are profound and far-reaching. As Dr. Natalie Cabrol, the renowned astrobiologist from the SETI Institute, emphasizes, the idea that life could travel between worlds isn't just possible. It's a hypothesis that deserves our serious scientific consideration. This perspective challenges our traditional understanding of life's origins and suggests a deeper connection between Earth and the cosmos than we previously imagined. Think about the countless meteors that streak across our night sky. Each one could potentially be carrying the building blocks of life, or even hardy microorganisms capable of surviving the harsh conditions of space. Every shooting star we wish upon might be part of a grand cosmic delivery system that has been operating for billions of years, connecting distant worlds through the exchange of life's fundamental components. The panspermia theory invites us to consider that we might all be descendants of ancient cosmic travelers, our deepest ancestral roots extending far beyond Earth's boundaries into the stellar seas. This isn't just about understanding our past, it's about reimagining our place in the universe and considering the possibility that life might be more interconnected and universal than we ever dreamed possible. As we delve deeper into this fascinating theory, prepare to have your perspective on life itself transformed, as we explore one of science's most intriguing possibilities about our cosmic origins. Journey with me back through time, 4 billion years into Earth's past. Our planet was barely recognizable then, a hostile, alien world where meteors continuously bombarded the surface, creating a spectacular yet violent display of cosmic fireworks. The skies glowed with impacts, oceans boiled from the heat, and the atmosphere was nothing like the life-sustaining mix of gases we breathe today. Yet within this seemingly destructive chaos, something remarkable may have been happening. These very meteors, which we once thought only brought destruction, might have been delivering the most precious cargo imaginable, the seeds of life itself. It's a profound paradox. The same cosmic bombardment that made Earth appear uninhabitable might have been the delivery mechanism for life's earliest beginnings. In 2019, scientists made a breakthrough discovery that sent ripples through the scientific community. They found organic molecules within meteorites that predated our entire solar system. The implications of this finding are staggering. Imagine holding one of these ancient space rocks in your hands. You would be touching organic compounds that existed before our sun burst into existence, before our planets formed, before Earth itself was born. These meteorites serve as time capsules, preserving the chemical signatures of a cosmos that existed long before our corner of the universe took shape. These organic molecules weren't simple compounds either. They were complex carbon-based structures, similar to the building blocks of life as we know it. Scientists found amino acids, nucleobases, and other sophisticated organic compounds, the very same chemical components that make up DNA, proteins, and other essential elements of living organisms. This discovery suggests that the basic ingredients for life might be abundantly scattered throughout the universe, waiting to find the right conditions to flourish. The age of these compounds tells us something even more extraordinary. The chemistry necessary for life didn't necessarily originate on Earth. Instead, it may have been brewing in the cosmic soup of space for billions of years before our planet even formed. This means that when we look up at the night sky, we're not just seeing distant stars and planets. We're looking at a vast laboratory where the chemistry of life might be constantly evolving and developing. What's particularly fascinating is that these ancient organic molecules survived their violent journey through space and Earth's atmosphere. They endured extreme temperatures, cosmic radiation, and the tremendous forces of impact, yet remained intact enough for us to study them today. This resilience suggests that life's building blocks are far more robust than we once believed, lending credibility to the idea that they could indeed survive long journeys between stars and planets. This cosmic delivery system may still be operating today. Every year, thousands of meteorites reach Earth's surface, potentially bringing new organic compounds from the depths of space. Each one is like a chemical message in a bottle, carrying information about the possibility of life beyond our planet and offering clues about how life might have begun here on Earth. Through this lens, Earth's violent past takes on new meaning. Rather than seeing those ancient meteor impacts purely as catastrophic events, we can now view them as possibly vital steps in preparing our planet for life. Each impact might have delivered not just physical material, but the very essence of what would eventually evolve into the rich tapestry of life we see around us today. The scientific evidence supporting the panspermia theory is both fascinating and compelling. In groundbreaking laboratory experiments, researchers have made remarkable discoveries about the resilience of certain microorganisms. These studies have revealed that specific bacteria, known as extremophils, possess an extraordinary ability to survive the harsh conditions of space that were once thought to be universally lethal to all forms of life. These remarkable organisms have demonstrated survival capabilities under conditions that mirror the extreme environment of space: intense radiation, complete vacuum, and temperatures approaching absolute zero. In controlled experiments, scientists have subjected these hardy microorganisms to combinations of these severe conditions, and amazingly, many have survived and remained viable. These extremophiles have earned their nickname as microscopic astronauts through their demonstrated ability to endure conditions that would be lethal to most other life forms on Earth. One particularly notable experiment involved exposing bacterial spores to the actual space environment. During the EXPOSE missions conducted on the International Space Station, researchers placed various microorganisms in special exposure facilities outside the station. After spending months or even years exposed to the unfiltered cosmic environment, some of these organisms remained viable, demonstrating that life, in its most basic form, could potentially survive long-term space travel. The implications of these findings are profound. If these microorganisms can survive in space, it lends credibility to the possibility that life could indeed travel between celestial bodies, protected within meteors or other space debris. These hardy organisms might serve as nature's own spacecraft, carrying the seeds of life across the cosmic void. Adding weight to these experimental findings, renowned astrophysicist Dr. Chandra Wickramasinghe's observation about the universe being replete with complex organic molecules has opened up new perspectives in our understanding of life's cosmic potential. His statement that life may not be a unique and isolated event, but rather a cosmic phenomenon, is supported by astronomical observations that have detected organic compounds throughout space, from interstellar clouds to the surfaces of comets. Recent spectroscopic analyses of distant nebulae and molecular clouds have revealed the presence of increasingly complex organic molecules, including amino acids, the building blocks of proteins. These discoveries suggest that the basic ingredients for life are not unique to Earth, but are distributed throughout the cosmos. The detection of these compounds in meteorites that have landed on Earth provides tangible evidence that organic materials can survive interplanetary travel. The discovery of these space-hardy bacteria and the widespread presence of organic molecules throughout the universe creates a compelling scientific framework for the possibility of life being transmitted between worlds. These findings don't just support the possibility of panspermia. They demonstrate its plausibility as a mechanism for the distribution of life throughout the cosmos. As our scientific capabilities continue to advance, we may uncover even more evidence supporting this fascinating theory about life's cosmic origins and distribution. The implications of panspermia, if proven correct, would fundamentally transform our understanding of life and our place in the cosmos. We often hear the poetic phrase that we are stardust, because the atoms in our bodies were forged in stellar furnaces billions of years ago. However, panspermia suggests an even deeper cosmic connection. We might be children of the stars, not just in our atomic composition, but in the very blueprint of life itself. The recipe for our existence, the complex molecular choreography that makes life possible, may have been written in the stars long before Earth was born. This cosmic perspective on life's origins opens up extraordinary possibilities about our relationship with the rest of the universe. If life can indeed travel between worlds, we might be part of a vast cosmic family tree, with branches extending across light years of space and billions of years of time. Every living thing we know, from the simplest bacteria to the most complex organisms, might share a common ancestor that originated on another world, making us all cosmic cousins in the grandest sense possible. Consider the profound implications for our search for life beyond Earth. If life can survive interstellar travel, then biological connections might exist between different solar systems and galaxies. We might be part of a cosmic web of life, where genetic information and biological innovations are shared across the vast distances of space. This would mean that life forms discovered on other planets might share fundamental similarities with Earth life, not through convergent evolution, but through a shared cosmic heritage. This concept also raises fascinating questions about the nature of life's evolution. If life can move between worlds, then evolution might not be limited to occurring on individual planets in isolation. Instead, we might be looking at a grand, universal process of evolution, where genetic innovations can arise on one world and spread to others through natural cosmic distribution mechanisms. This would suggest that life's diversity and complexity might be driven not just by earthbound processes, but by contributions from across the cosmos. The possibility of panspermia also challenges our conception of life's resilience and adaptability. If microorganisms can survive the harsh conditions of space travel, the extreme temperatures, radiation, and vacuum, then life might be far more robust and versatile than we previously imagined. This resilience would suggest that life, once started, might be nearly impossible to extinguish completely, persisting and spreading throughout the universe like an unstoppable cosmic force. Perhaps most profoundly, if panspermia is true, it would mean that we are not just observers of the cosmos, we are its direct products and ongoing participants. Every living thing on Earth would be a testament to life's ability to traverse the cosmic void, to survive against incredible odds, and to flourish in new environments. We would be living proof that life finds a way, not just to survive, but to cross the seemingly insurmountable gulfs between stars and planets. This cosmic perspective on life's origins and distribution could fundamentally change how we view our role in the universe. Rather than seeing ourselves as isolated beings on a lonely planet, we might better understand ourselves as part of a grand cosmic experiment in life's evolution and dispersal. Our responsibility would extend beyond Earth's boundaries, as we would be custodians of a cosmic heritage that has been billions of years in the making. The panspermia theory, while captivating, faces significant scientific challenges and controversies that demand rigorous examination. One of the most pressing concerns revolves around the extreme conditions that microorganisms would need to survive during their cosmic journey. The violent entry through Earth's atmosphere presents particularly daunting challenges. Temperatures can reach several thousand degrees Celsius during atmospheric entry, creating conditions that would seemingly destroy any form of life, no matter how resilient. Critics argue that even if microorganisms could survive the harsh conditions of space, the process of entering a planet's atmosphere would be catastrophic. The intense heat and pressure generated during atmospheric entry would theoretically destroy any organic material, let alone living organisms. However, proponents counter this argument by pointing to the discovery of organic compounds in meteorites that have survived atmospheric entry. They suggest that microorganisms could potentially survive if they were sufficiently protected within the interior of larger meteorites, where the outer layers would act as a heat shield during entry. Another significant challenge lies in definitively proving that life originated elsewhere rather than on Earth itself. This creates a classic chicken or egg scientific dilemma. How can we definitively determine whether life began here and then evolved, or arrived from space and then evolved? The evidence we find could potentially support both scenarios. Critics argue that the presence of organic compounds in meteorites doesn't necessarily prove that life came from space. These compounds could have formed through natural chemical processes anywhere, including on Earth. The contamination problem presents another serious challenge to researchers. When studying meteorites for signs of extraterrestrial life or its precursors, how can we be certain that what we're finding isn't simply contamination from Earth? This challenge becomes particularly acute when dealing with ancient meteorites that have spent considerable time on Earth's surface, potentially becoming contaminated with terrestrial organic matter. Skeptics also point to the vast distances between stars and the incredibly long time frames involved in interstellar travel. Even if microorganisms could survive the harsh conditions of space, could they remain viable over the thousands or millions of years required to travel between star systems? The radiation exposure alone over such extended periods poses a significant threat to any form of life, no matter how resilient. The theory also faces challenges from proponents of traditional abiogenesis, the idea that life originated from non-living matter on Earth through natural chemical processes. They argue that Earth's early conditions provided everything necessary for life to emerge, making the need for extraterrestrial origins unnecessary. The presence of organic compounds and suitable environmental conditions on early Earth could have been sufficient for life to arise independently. There's also the question of statistical probability. While space is indeed vast and filled with organic compounds, the chances of life-bearing materials not only reaching Earth but doing so in a way that allows for successful colonization seem remarkably small. Critics argue that this mathematical improbability makes terrestrial origins more likely than extraterrestrial ones. The method of transport itself raises questions. Even if we accept that microorganisms could survive in space, what mechanism would efficiently transport them between star systems? Solar winds and radiation pressure might not be sufficient to propel biological material across interstellar distances in a way that maintains viability. Additionally, there's the challenge of explaining the apparent uniqueness of Earth's life forms. If life regularly travels between worlds, why do all known living organisms on Earth share such similar biochemical foundations? Wouldn't we expect to find more diversity in basic biological systems if life had multiple cosmic origins? These challenges don't necessarily invalidate the panspermia theory, but they do highlight the need for continued research and investigation. As our scientific capabilities advance, we may develop new ways to test these hypotheses and address these fundamental questions about the origins of life. The controversy surrounding panspermia serves as a reminder that in science, even our most intriguing theories must stand up to rigorous scrutiny and evidence-based analysis. The panspermia theory stands as a profound reminder that the boundaries between Earth and the cosmos are far more permeable than we once believed. As we gaze up at the night sky, we might be looking not just at distant points of light, but at the very cradle of our biological heritage. The stars above us may represent more than just the forges where our atomic components were created. They might be the source of the complex molecular choreography that we call life itself. This theory fundamentally reshapes our understanding of our place in the universe. Rather than seeing Earth as an isolated biological experiment, we might better understand it as part of a vast cosmic laboratory where life's possibilities are endless and interconnected. The meteor showers that streak across our night sky might not just be celestial light shows, but glimpses of the same delivery system that could have seeded our world with its first living organisms. The implications of panspermia extend far beyond scientific curiosity. They touch upon some of humanity's most fundamental questions about our origins and our connection to the cosmos. If life can indeed travel between worlds, then we are not just observers of the cosmic dance. We are active participants in a grand biological narrative that spans the entire universe. Every living thing on Earth might be evidence of an ancient journey through the stars, making us all, in essence, descendants of cosmic travelers. This perspective also transforms our approach to the search for extraterrestrial life. If life can survive interstellar journeys, then biological connections might exist between different solar systems and galaxies. The discovery of life elsewhere in our cosmic neighborhood might reveal not just distant cousins, but direct relatives sharing our cosmic genetic heritage. As we continue to explore and understand our universe, the panspermia theory reminds us to maintain an open mind about the possibilities that exist beyond our traditional understanding. The story of life might be far grander and more interconnected than we ever imagined. Each new discovery in space exploration and microbiology adds another piece to this cosmic puzzle, potentially bringing us closer to understanding our true origins. The elegant simplicity of panspermia, the idea that life might be a cosmic phenomenon rather than a planetary one, opens up endless possibilities for future research and discovery. It suggests that wherever we look in the universe, we might find echoes of our own biological story, written in the language of organic chemistry and carried on the solar winds between the stars. As we conclude our exploration of this fascinating theory, we're left with a profound sense of connection to the cosmos. Whether or not panspermia ultimately proves to be the explanation for life's origins on Earth, it has already succeeded in expanding our perspective about what's possible in our universe. It reminds us that we are, in every sense, children of the cosmos. Our matter, our energy, and perhaps even our very life essence originating in the vast expanse of space. This cosmic perspective challenges us to think differently about our role in the universe and our responsibilities as conscious beings who can contemplate these possibilities. As we continue to explore these profound questions, we might find that our search for understanding leads us not just to scientific discoveries, but to a deeper appreciation of our place in the cosmic web of life. The story of panspermia, like the story of life itself, remains an ongoing narrative, full of possibilities and mysteries yet to be uncovered. As we continue to explore and understand our cosmic surroundings, we might find that we are part of a much larger story, one that extends far beyond the boundaries of our planet and deep into the cosmic ocean that surrounds us.